So I think we have no questions in the discussion forum for this topic as of now, but we have one question in the response sheet, students' response sheet which we got. So if you have any questions, please unmute and you can ask. Otherwise, use the live chat.
Thanks, Amrita. Maybe we can wait for just a couple of minutes, see if a few more people join. The question that came in through the Google form was from Dilip.
I think you're on mute.
I'm
We
not on
can't
mute.
hear you.
Can you hear me now?
No.
You're audible.
Oh, sorry. I think I'm not.
Audible now?
Yeah, yes, you are.
Oh, okay. I hope Amrita can also hear. So anyway, we'll wait for a couple of minutes and then we'll take whatever's there. And if you don't have many questions, I'll just do a quick recap also of the lectures. But we'll start in about 5:03, something like that. My volume is low. Okay, is that better?
Yeah, it is.
Great, thank you.
So shall we start the question in the response sheet? Yes.
Yeah, I'm just waiting to see if the person who asked the question, Dilip, if he turns up. Can you hear me, Amrita? Can you hear me?
Yeah.
Oh, okay, good.
Yes.
Yeah. So I said we start in at about 3 minutes past 5. So yeah, we'll just wait for another minute. And others, if you can mute yourself, unless you're asking a question. Dr. Hariom, you can just mute yourself. When you want to ask a question, you're welcome to unmute and ask. Okay. All right. So let me start not by addressing a particular question, but I think, the topics that I've been dealing with, framing a research question, methods of science, firstly, then framing a research question, then study design, and now data visualization and analysis. I think those of us who come from a very strong natural history background and care about the living bird in its habitat and so on, we may ask ourselves, why are we doing all this maths and stats sort of thing? Isn't it more important just to be out there observing the bird and so on? And of course, the answer is yes, that's tremendously important. But when we're doing scientific research, we want to say something more about the world, in this case, birds. And that means that if you want to say something about Sarus cranes or about weaver birds or something like that, you need to, in some systematic way, go and collect information. And then using that information, you want to kind of make some general statements. You don't want to say only that I watch these 5 Sarus cranes and this is what these 5 Sarus cranes do. You want to be able to say that I watch these 5 or 20 or whatever, 30 Sarus cranes. And because of the design of my study, the careful design and the way I've analyzed it, I can make a more general statement about Sarus cranes, their behavior or their song or something like that. A more general statement than just about these 5 or these 30 individual birds alone. And so inevitably, we have to come, and engage with these concepts of study design, data collection, what allows you to generalize beyond the particular sample that you've taken, the particular birds you've observed, and so on. So I know it's a bit tough going, and especially this last couple of lectures that that you've seen of mine, the data analysis part is tough going. But if you are an enthusiast, I completely understand if you just skip it, say forget it, I'm not going to. But if you think you might want to engage in bird research or ecological research of any kind, then it's really important that you engage with these ideas about quantitative data analysis, visualization, and really understand the nuts and bolts, why we're doing it, what is the logic behind some of these best practices or study design or analyses and so on. So that's kind of vital. You won't be able to progress much in a research career if you don't understand those things. But if you're not doing it into a research career, that's perfectly fine. I would skip it if I were you. So that's just by way of background. Amrita, I did mention if you have questions, please, you can about the data visualization and analysis part, please do type them in the chat box. If you would like to ask a question verbally, you can just raise your hand and I'll call on you, and then you can unmute yourself and speak. So there was a question. I'm just seeing if Dilip joined, because Dilip D'Souza asked a question through the form. Amrita, you said in the discussion forum there aren't any questions at the moment, right? Just looking at the discussion forum. Okay, there's something about x-axis. Sorry, just give me a few seconds. No, not for me. All right. So the question that Dilip put on through the Google form was about the sample size. So typically when one goes out, and I can read out his question so I don't get it wrong. There's some preliminary, and then when observing birds to learn about some feature phenomenon, for example, feeding habits at different altitudes, what kind of sample size do you typically get? And so if you are into research, all of you, please realize that sample size in most situations is under your control. So you would, rather than asking what sample size do you typically get, you would ask yourself, what sample size should I aim for? Now, at the very extreme, you can imagine that if I'm studying feeding habits of, let's say, there's a bird called greenback tit at different elevations in the Himalaya, right? Let's say at 1,000 meters, 2,000 meters, and 4,000 meters, suppose. Now, at the very extreme, you can imagine I want to understand if their feeding habits change, and I observe one bird, one individual greenback tit at 1,000 meters, and then one more at 2,000 meters, and one more at 4,000 meters. And I saw that their feeding habits differed. Let's say the greenback tit I observed at 1,000 meters was feeding in some shrubs, so low down in the near the ground. At 2,000 meters was feeding on the ground, and at 4,000 meters was feeding up on the branches of a tree, suppose. Now, you would, I hope, agree with me that that's not sufficient to make any general statement about how greenback tits change their feeding habits from 1,000 to 2,000 to 4,000, because I've only looked at one bird from each place. And that one bird I've only observed, let's say, for 10 minutes, right? So I have a 10-minute sample from one individual bird at each of these three elevations. So that's clearly not enough, no? Because if I were to make some generalization, I could very easily be misled. I could make a wrong statement just because there's obviously variation among birds in their feeding. Dilip, this is your question being addressed, your question in the form. So at the one extreme, if you look at only one bird and its behavior and make some statement, you're going to be misled. I hope that's clear. If it's not clear to everybody, please, do raise your hand and ask. So we can spend 10 minutes at each elevation, look at one bird and come to a faulty conclusion. At the other extreme, you can spend years and years, and at every elevation, you could you could find, let's say, 100,000 different birds. You'll have to travel a lot to find 100,000 different birds. So try 100,000 different birds at elevation 1,000 meters, 2,000 meters, and 4,000 meters. And that might be overkill, right? Maybe we don't need to observe so many birds to make some generalization. Yeah, this is your question, Philip. To make some generalization about the feeding habits of greenback tits at different elevations. So somewhere between one bird, your sample size, and 100,000 or a million or whatever it is. So the question is, what should that number be? You'll hear very often a number being generally discussed, saying that you should have a sample size of at least 30 in each category. So in this case, elevation is a category. So I 30 birds, observation of 30 birds in one elevation, 30 in another, 30 in the third. Now, this 30 is it comes from a particular logic. The 30 comes from the logic that, if you remember from the lecture, in many cases, if we would like to imagine that the sampling distribution, that is the distribution of sampling means, follows a normal distribution. And the reason we can assume that sometimes is because of something called the central limit theorem. And the central limit theorem says that the distribution of means of something that we measure typically follows a normal distribution. So in this context, suppose I was looking at, let's say, the size of greenback tits, the length of let's say the body mass, the weight of greenback tits, 1,000, 2,000, and 4,000. And I took a sample and I calculated the mean from 1,000. And I took another sample and calculated the mean, and took another sample and calculated the mean, all from 1,000 meters elevation. The distribution of those means are going to be normal. That's what the central limit theorem says. And it says that the distribution of those means will be normal pretty much regardless of the underlying distribution. That is, even if the distribution of actual body masses of the greenback tits is not normal, the distribution of their means is going to be normal. And especially if the distribution of body masses, the original distribution, is not very far from normal, if it's not very skewed, and if we have large enough sample size. So what is large enough sample size? Well, roughly 30 is what people say. So this rule of thumb that you should have at least 30 samples from each category comes from the normal distribution and the Z and T distributions. But if you remember from my lecture, actually, the precision with which we can say something about the mean of the body mass of tits is dependent on the sample size, one, but also on the variation in the population. Suppose the weight of these birds is very variable. Some of them are only 5 grams, others can be up to 20 grams. If the weight is very variable, then to capture the mean, the population mean, we need a large sample size. If the variation in the weight is small, let's say all these birds have a body weight of between 9 and 11 grams. Actually, it's more like between 18 and 20 grams, let's imagine. It's a very small range. Then, even with a small sample size of, let's say, 10 or 20, we should get a good handle on the population mean. Because after all, the population mean can't vary between 18 and 20. But if the weights of the birds varies between 5 and 30, then we need a larger sample size. So, unfortunately, Dilip, the answer to your question is what sample size do I need? And by the way, this is a question that all research students, all researchers keep asking. This is what I want to do. What sample size do I need? And the frustrating answer is, it depends. Like many useful answers, it's a frustrating answer. It depends. But in this case, we know exactly what it depends on. It depends on the amount of variation in the population in whatever you're measuring, let's say body weight, and it depends on how much precision you need. Do you want to capture the population body weight, in a range of plus or minus 0.5 grams, which is quite a precise measurement, so we'll need a large sample size, or plus or minus, let's say 5 grams, which is very, very low precision, and we can get away with a smaller sample size. And in my lectures, there's some examples for how you can calculate if you define what precision you need, and you have done some pilot study where you know the standard deviation in the population, which is the measure of the variation in the population, then you can calculate what sample size you need in order to achieve that desired precision. Remember, the variation in the population is not under your control. That is just a given. That's part of the property of the population. The sample size is under your control, and the precision that you need depends on some other kind of, other considerations. For example, if I want to know what is the population size of Great Indian bustard, because it's a threatened species and because the numbers are low, I want to capture my best estimate in relatively narrow bounds. I want to say the population is this, let's say plus or minus 20 birds. Let's say the population is 120 plus or minus 20, which means if it's a 95% confidence interval, that means that we are more or less confident that there are between 100 and 140 birds. And that's maybe a reasonable precision. But for Great Indian bustard, we would not be happy with plus or minus, let's say 70 birds. So my best guess is 120, same as before. But it could vary between 50 birds and 190 birds. That's much too large a confidence interval. That's much too broad an estimate, because if it's as low as 50, then all alarm should be ringing. We should be pulling out all, 50 birds is on the verge. 120 is not far, but 50 birds is really, really bad. So we don't want such uncertainty between 50 and 170. We need something much more precise. So you can see, I hope, that the precision that you want out of your study is something that you have to define. Otherwise, you won't know what sample size to use. And you have to define it on the basis of what that number is going to be used for. Is that number going to be used for some action in the future, especially in conservation and so on? Is it going to trigger some action? If the rate of population decline is more than X amount, then it would trigger, for example, an upgrading of that species status in the IUCN Red List. So we want to, if it looks like it might trigger that, we want to have a fairly precise understanding of the rate of population change. We don't want to throw up our hands and say, well, it could be changing rapidly, but it's very uncertain. It might not be changing at all either. So the rate of population change could be from 0% per year to, let's say, minus 50% per year, if you have a very broad confidence interval, very low precision. So that means you don't know whether it's not changing at all, the population, it's stable, or is declining as fast as 50% per year. This is not a situation you want to be in. So I think it is, yeah, it is. By the way, science, when people say science and art, Dilip, you said, as though science is objective completely. This is what some people think and some people claim, but that's not true. There are many subjective decisions that need to be made. When you design a study and implement a study, unfortunately, well, I don't know if it's unfortunate, but many people think it's unfortunate, you can't simply follow a recipe book. There are good practices that you should follow, you should know about and follow, but there are also subjective decisions about what precision you need, or in what precise way you might measure the body size of something, or in what precise way you might look at the hormonal, the amount of circulating testosterone or whatever hormone in a bird's blood or something like that. So science is a mixture of the objective and the subjective. There's a lot of room for creativity, and the best scientists are extremely creative. Otherwise, some people have this notion that doing research is just a mechanical thing, that there's a recipe book, you follow the recipe book, and that's it. And so sometimes we think of the, arts as being creative, and it's not stated, but the implication is that science is not creative. But actually, both science and art have elements of rationality and subjectivity and creativity in them. So in any case, that's a bit of a side point. We were talking about sample size. So just with that, just to come back and summarize. So unfortunately, the answer to what sample size do I need is it depends, but at least we know what it depends on. It depends on just a couple of things. And those things are things you can either measure, like the variation in the population. You can do a pilot study and measure that to understand how much variation there is. And a combination of that together with a decision that you have to make about what kind of precision you need if your study is to be successful. A successful study is, in my mind, is not one in which the results that you find are in accordance with your expectations or in accordance with theory or whatever else. A successful study is one that has sufficient precision that you can make a strong statement at the end of it. That strong statement can be either way. The strong statement could be that I'm pretty sure that the population is increasing, or I'm pretty sure that the population is stable, or I'm pretty sure that the population is decreasing. In any of that covers all possibilities. So to my mind, the success of the science, the success of the conservation is different. The success of the science depends on whether you can make a strong statement. Any of these three would be fine. Unsuccessful research would be that, well, my best guess is that the population is increasing, but my confidence intervals are so wide, it spans from decreasing at 20% per year to increasing at 70% per year. That is such a wide confidence interval, such low precision, that I can't make a confident statement at all. I have to make only a very loose statement. And essentially, you could argue that if you make such a loose statement, then you haven't really learned anything. So you spent all that time and money doing the research, and you have come back without actually adding to our knowledge. So this question about precision is extremely important. All research students over here, I think you really need to engage carefully with it. What is it that will allow us at the end of our study to make a strong statement, regardless of what that statement is? It needs to be a strong and confident statement. And in most cases, it boils down to what your precision is. And the precision in most cases boils down to what your sample size is. So you really have to think carefully about sample size. So that was a long-winded answer to the question that Billy put, but thanks for that, Billy. If you have the correct sample size, will you always be able to make a definitive statement? No, Yasmin. To make a definitive statement, you need to have a combination of a whole bunch of things. So sample size and precision is one. But suppose you want, like, for example, you want to make a definitive statement about cause and effect, about cigarette smoking and lung cancer, right? If you don't have the appropriate study design, suppose you don't do an experiment, then you'll never be able to make a definitive statement about cause and effect. Suppose I need to make a statement about cause and effect between diclofenac and vulture declines. I can do a lot of research to find the circumstantial evidence that, yes, as diclofenac became more prevalent, then vultures started declining in those areas. Yes, we see that carcasses of cattle have diclofenac in them. Yes, we see that vultures that have died have diclofenac in their tissues. None of this they're all point in the same direction, and they all give very strong hints that diclofenac is a cause of vulture decline or vulture mortality, but it doesn't prove it. So the only way to prove it is to do, as the researchers did, is do a clinical study, right? Where you feed some vultures, unfortunately, diclofenac in the same dose that you would get in nature, and they found that they died. And of course, that's an entire separate thing, a very interesting story about how they did it and where they found the vultures to do it on, and how they decided. They stopped at a very small sample size because they said that the evidence was so clear because the vultures died so quickly after being fed meat with diclofenac that there was no point continuing. I think they just did 4 vultures, 3 or 4 vultures. Statement, multiple things are, and if your study design is not right, let's say you have collected a biased sample. If I'm going out and asking people their opinions on conservation, I want to ask, do you like snow leopards or do you like tigers or not? And why don't you like tigers or not? We know that people, when they answer, they may not tell us the full truth. They often tell us what we think what they think we want to hear. Or there may be other reasons why they may not tell us the truth. So that's called measurement error. That is, we are not getting the appropriate response. Secondly, the kind of people who we ask these questions to, are they a representative sample of the population? In many cases, when social scientists do research of this nature, they're almost always asking men, because men are the ones who tend to be comfortable talking to outsiders. And women in rural India tend to be less comfortable talking to outsiders, especially if those outsiders themselves are men. So then we are biased. Sampling is biased because we are asking the men. So what we're coming back is maybe we can make a definitive statement about what men think about tiger conservation or whatever else in rural India, but we can't say make a definitive statement about people in general. So unfortunately, there are a number of different ingredients. All the ingredients have to come together if we want to make a definitive statement. One of them is sample size, but it's not the only one. Yeah, that's why doing research is pretty complex. That's why this series of long lectures for all of you, trying to talk about the good practice or the different things to think about while planning and executing your research project. It is fairly complex to think about, especially when we implement it in the real world. The real world with all its variation and all its complexity. In a toy world, in the lab, for example, when people do experiments in the lab, even then it's complex. But because we are taking the situation out of nature into a controlled environment, actually things become quite a bit more simple. But when we are going out into the real messy world, and we have to take account of that messiness, but at the same time we want to make clear and definitive statements, then we really have our work cut out for us. Yeah. So there was an earlier question. Explain the term bootstrap. So yeah, so the word bootstrap itself, as applied to statistics, comes from an English phrase, idiom, which says to pull yourself up by your bootstraps, which of course you can't do. No, you can't pull yourself up with your bootstraps. Your boots remain firmly rooted to the ground. But it means making do with what you have. So doing the best with what you have. And in our case, in the statistics we've been talking about, we've collected a set of data. Let's say we've collected body weight of 50 greenback tits in 1,000 meters elevation in Himachal Pradesh. So that's all we have. We have 50 body weights. And now we have to talk about what could be the, and we are assuming that everything upstream from that was all done perfectly, right? We sampled those 50 individual birds in a way that's representative of the population. We didn't sample them in a way that we caught the most active birds, because maybe the most active birds have a different body weight on average than those birds that are not very active, right? If we sample them because of this, then we'll be biasing our estimate, etc., etc. We're imagining those 50 birds are collected, are caught and measured and released in a way that is representative of the population. We assume that the way in which they were measured, there was no measurement error or measurement bias in that. So the body weights that we have actually measured are accurate and precise. And now we have these 50 numbers and we have to pull ourselves up by a bootstrap, do the best with these that we can. And essentially, there are two things we want to understand. Well, there's one main thing. We want to understand what is the population mean, some population parameter, let's imagine population mean, of greenback tits at 1,000 meters elevation. So our estimate, our best guess of the population mean of the body weight of these birds is the sample mean, right? So we simply just take 50 data points, take the mean of those 50. That's our best guess. But remember that best guess also comes with some uncertainty. And we want to know, is there a large uncertainty? Is it a small uncertainty? Is that measurement very precise or is it imprecise, which is the same way of saying that? And that's where the bootstrap comes in, right? The bootstrap says, okay, we have these 50 birds. As far as we can tell, this is our best understanding of what the population looks like. Although we've got only 50 from those the population. So suppose we imagine that these 50 body weight measurements represented the actual distribution of body weight measurements in the population. And we have taken a sample size of 50, of course. But tomorrow or day after, or somebody else could have taken a different sample of 50. And somebody else could have taken a different sample of 50. How similar or different would the means of these multiple samples be? And we try and answer this question through Bootstrap by putting those 50 body weight numbers in a box, in a bin, in a basket, and then drawing 50 numbers with replacement. So in other words, as we sample the population, we are not changing the distribution of these numbers. So that is what would happen if we took a chit, wrote down the number and put that chit back, and took another chit, wrote down the number, put it back, and did so 50 times. And we'll come up with a different set of 50 numbers, all drawn from those original 50. Some of the body weights will be missing, some of the body weights will be duplicated, and so on, and that's fine. But it just represents what a possible sample of 50 could be from an underlying population that looked like those 50 that we had originally sampled. So that gives us a sample mean, one sample mean. That's one bootstrap and one bootstrap mean. And then we do it again and calculate another bootstrap mean and do it again and calculate another bootstrap mean. And if we do that many times, 10,000 times, let's say, we'll have a distribution of bootstrap means. And from that distribution of bootstrap means, we get an idea about how variable our means could have been. If all the bootstrap means lie between 18 and 20 grams, right? That means that we've estimated our population body weight with quite a lot of precision. But if the bootstrap means lie between 5 and 30 grams, that means that our estimate is quite uncertain. And in the lecture, I show you how from that distribution of bootstrap means we can take the quantiles, let's say the 2.5% quantile on the left side and 19.5 on the right side, and those numbers will define the 95% confidence interval, which in turn is a measure of our precision, right? So Bootstrap is this computationally intensive way of trying to understand what our precision is in our population estimate and our best guess of the population based on resampling and resampling and resampling the data that we already have. Yeah, you unmuted. You want to add something? Malay, you wanted to add something?
Yes.
Yeah. Yeah, go ahead if you want to say something. Or if not, then please unmute your microphone.
Okay, thank you.
Yeah. Okay, I hope that was somewhat understandable for all of you. Amrita, you unmuted? No. Any other questions about the visualization and analysis lecture? I'll wait till somebody has a question because our throat is pretty dry.
Hi, Suhel.
Yeah,
Am I now? Yeah. Yes. I think there is one question in the discussion forum which we got now.
I'll take a look.
Yeah. from Vignesh Pujari.
Okay. Okay. So this is tough because he has linked to the beginning of the video of the lecture, and I'm unable, I don't know what exactly. Oh, at 01449 is what it says. Oh, okay. Sorry, guys, I'll just have to go to that 01449. It's near the end of the lecture.
Hello, sir. This is Vignesh.
Oh, you're there.
Yes, sir. Actually, the doubt is about the summary where you summarize the entire lecture. At that time, you give examples about the pilot readings and all. That I was a bit like didn't understand a bit about how it's proceeding.
So essentially, Vignesh, I don't know if you been here from the beginning of this live session?
Yes, sir. Yes, sir.
Okay. So I mean,
So bit a bit I'm able to understand now, but just one.
yeah. So in the context of this particular topic, which is data analysis and precision and so on, the reason to have a pilot study, to go out in advance and measure not 50 greenback hits, let's say, if that's your final sample size. Let's say you do a pilot study and you measure 10 or 15 of them. And the reason for doing that is to understand what the variation in the population is, so that you can better plan what final sample size you need based on what precision is required. Okay. So in the absence of doing a pilot study, you won't know what the variation is in the population. And if you don't know what the variation is in the population, you don't know what sample size to plan for. And if you don't know what sample size to plan for, then you don't know how many days you need to be out in the field, or how much effort you need, or if you're catching them with mist nets, let's say, then, do I need one mist net alone? Is that enough? Or should I have to put 20 mist nets out there? How many days and things like that. So that's the importance of doing a pilot study from the narrow perspective of what I've been speaking about in this lecture. But generally, for a lot of other reasons, it's very useful to go and do some small pilot work in the landscape, if you're doing field work in the landscape that you intend, because it'll give you some idea about the logistics. Where is there a place to stay? How will I move about? Where do I get food? All these are very, without these things, we can't do work. But they also give you an idea about the ecology of the place. The kind of idea and the question and the plan that you had conceptually, theoretically back, in your university or wherever you are, once you get to the field, you might realize, oh my gosh, things are very different over here from what I thought or expected. And some of the ideas that I wanted to try out, or some of the reasoning, some of the logic I was using to come up with these ideas, they don't apply in this landscape. And then you have to go back to the drawing board and rework your study. So better to do a pilot study, a visit, and ideally collect some data. And with that intelligence, with that information, come back and not just figure out what sample size you might need, but also check whether the entire logic and the plan that you had made originally, whether that still holds. Most people who don't do such pilot studies, and if they are not already familiar with the landscape or the species or the place that they're going to work in my experience, land up in a place, realize that things are different, and have to quickly on the fly make changes to their plan. So it's better to build in some kind of trial testing, or I'm calling it pilot study or visit, so that time is budgeted and you can go back, talk to your guide or whatever, or whoever's advising you, and make a plan, and then go to the field for your actual study. So yeah, that was the pilot part of it. Yeah, that's really strongly recommend that.
Okay, sir. I understood. Just one small doubt, like, how do you go with, like, let's say if you are doing some estimation of some insects or something in the field, how long to take like pilot reading, like how to decide whether, like, how many samples to take, or like for how long to do the pilot readings?
Hmm, hmm, hmm.
How
So,
will
I mean, yeah. Yeah. So I think, you'll have some idea if you're doing insect estimation. There are many different ways to do it. There are pitfall traps, and you can bag branches, or you can do sweep netting, or you can do, like for moths, you do the blue lighting, the UV screens in the night, and so on. So whatever is appropriate for the particular insects that you want to study. What you would do with the pilot study, you would use that. So firstly, suppose you don't know. Is this method going to work, or which method should I use? Then that pilot study is to figure out what method to use. So you might put out some pitfall traps, you might do some sweep netting, you might do some night lighting, you might whatever else. And then you look at, am I getting the beetles that I need, or am I getting the moths that I want? Is this more effective at getting my taxon, the beetles, if it's beetles, or is that method more effective? So that's one thing. You just have to try it out for several days, not just one day, not just once, but multiple times. So try it out multiple times. Um, so I would say maybe spend a week or 10 days, uh, repeat your procedure multiple times. And through that, you're also collecting data, and you can calculate some amount of variability. Like if I suppose pitfall traps don't work very well. Pitfall trap is like a plastic tray that you'll dig a little hole in the ground and put the tray such that it is the top of the tray is at the level of the ground, and you fill it with water and some soap. So whatever creatures are kind of walking along the ground, they stumble into the tray, fall in, and because of the soap, the surface tension is broken, and so they can't get out again. Unfortunately, they drown and they die. This is just a feature of pitfall traps. Suppose you put out 20 pitfall traps and leave them for a day, and after a day, you find that one trap has 5 insects, 18 traps have no insects, and the last one has got like 1 insect. That's probably not a very effective way of sampling insects. So you'll have to move to something else, right? Because you get lots of zeros. Zeros is data, but it's not very informative data. So you might need bigger pitfall traps, or you need to put them in a better location. Or pitfall traps may not be the appropriate thing at all. So you know what I mean? So there are multiple things that you'll have to figure out what are the open questions that I need to know the answers to before I can implement my study. Whatever those open questions are, a pilot study is useful to answer and address those.
Okay, sir, got it. Like it's basically trial and error method, and then trying out different methods and finding which one is more suitable and going.
Yeah. I mean, ideally, it won't be completely trial and error, because
Yeah.
you have read other papers that have done something similar. It could be in India, it could be anywhere else in the world. And you'll see that, in Malaysia, when people are doing this kind of work, this is the kind of method they use. But you may have never used the method. So you want to ensure that when you go in the field, you actually know how to use that method and it's working properly. So you go and try it out. So trial and error, sometimes the implication is I'm just trying randomly various things. But I know what you mean. It's not randomly various things. It's
Yes.
trying different methods from what the literature or other
Literature.
experience said. Yeah,
Yeah.
absolutely.
Got it, sir. Thank you, sir.
Yeah, sure.
Malai
Okay.
has asked one more question.
Yes, standard error and standard deviation. I saw that. Yeah. Okay. So this I think repeated in the lecture. Please look at that section multiple times. I'll say it once more, but it's really, really, really important all of you understand the difference between standard deviation and standard error. And it's confusing because the standard error is a kind of standard deviation, but the two of them mean very different things. So if I were to take the body weight of these birds, 50 birds, and I calculated the standard deviation, right? That is body weight of every bird minus the mean body weight, square that, and take the sum of those squares divided by the sample size minus 1 and take the square root. Okay, you know the formula for standard deviation. Then that standard deviation of the body weight gives us an idea of the variation in the population. That is variation in body weight from bird to bird in the population. So standard deviation is a measure of variation in the population. Standard error is the standard deviation of those bootstrapped sample means. Remember, we put 50 birds, we drew 50 with replacement from our basket, and then we calculated the mean, did that again, did many times, 10,000 times or whatever. And we have now 10,000 bootstrap means. The standard deviation of those 10,000 or whatever number bootstrap means, that is a measure not of the variation in the population, but of the precision of your estimate of the mean. Because if the standard deviation is large, that means you can get bootstrap means that are very different from each other. If the standard deviation is small, I get bootstrap means that can't be very different from each other. They're very similar to each other. That means I have high precision when I'm trying to make a generalization about the population. So on the one hand, we have standard deviation of the raw data, which is a measure of variation. On the other hand, we have standard deviation of the bootstrap means, because we were talking bootstrap earlier. And that's a measure of the precision of your estimate of the population mean body weight. So the standard deviation of the bootstrap means is called the standard error. So just remember, standard deviation by itself is the measurement of variation in the population. Standard error is a measurement of precision, which we get or we can get by calculating the standard deviation of bootstrap means. But if we can assume that the center limit theorem holds and the distribution of possible sample means is normal, then we can calculate the standard error directly, as I mentioned in the lecture, by taking the standard deviation divided by the square root of the sample size. So there are different ways to arrive at the standard error. But please remember, standard error is a measure of the precision. So that's why we take our like 1.96 times standard error or something like that. The confidence interval is related to the standard error. But the standard deviation is so we can have a very large standard deviation, that is large variation in the among the population. But if we have large enough sample size, then we can have a small standard error, which means our precision is large. So in the same study, you can have large standard deviation, but small standard error, provided that your sample size is large enough, so that the precision of your estimate of the population mean is high. That is, the confidence interval is low. Okay, so this is better explained with reference to the slides and so on. So please, do look at the video again, just that part that relates to standard error. Please don't get confused between these two. Some people think that they're interchangeable. People are confused about what to put in their figures when they draw graphs, and should I put the standard deviation and standard error? And the answer is, if I want to show variation among the samples, the variation in the population, then I put the standard deviation. If I want to show the degree of precision of my estimate, then I put the standard error. My voice is fading now, so I think we may have to end a few minutes early. I had a throat infection last week, so I think there's some lingering effects of that. If there are any like one last burning question, there must be many burning questions, but one last one, we can take that, and then we can close. Okay, no questions. Thanks to the subset of you who's sticking with this. It's a difficult topic, but do, as I say, wrestle with this and make sure you understand if you are trying to pursue a research career. If you are an amateur birdwatcher, an enthusiast, and you don't intend to do research, although enthusiasts can do research and very good research as well, and have done so. But if you don't intend to do research in the future, you're very welcome to ignore this lecture. But those of you in the research track really need to wrestle with this topic about data visualization and analysis. Yeah. So with that, then we'll draw it to a close. Thank you so much. Thanks all. Thanks, Amrita, for facilitating this. And I'll be in touch over email later. At the end of the course, we'll send a wrap-up email to all of you. But this is the last lecture from my side. All the best for the rest of the course and the final exam. Take care.
Thank you so much, Suhel.
Yeah.
Thank
Bye.
you so much. Thank you,
Bye.
everyone joining. Bye.